Hello everyone, I am Aditya Nittala, Assistant Professor in the Department of Computer Science at the University of Calgary. On behalf of my students Peter and Purna and our co-author Jaeyeon from UNIST, I am presenting our work on augmenting on-body touch input with tactile feedback through fingernail haptics. The human body offers a large and readily accessible surface for always available eyes-free interaction. For these reasons, sensing touch input on the body has received considerable attention in the HCI community. However, the key assumption attributed to on-body touch input is that the skin that is being touched provides natural tactile feedback when interacting with the body. This is analogous to mobile devices during their infancy. There was touch screen but no haptic feedback. Then several research works showed that coupling tactile feedback with touch input can create highly expressive interactions. That is very much evident from our daily interaction with mobile devices. For instance, when we perform a text entry task, we get a subtle tactile feedback to indicate that a key has been pressed. Similarly, tactile feedback has also been shown to be very effective for enhancing touch interactions in automotive interfaces too. In line with this theme, we propose the haptic augmentation of on-skin interfaces, where our aim is to augment on-body touch input with tactile feedback. Instead of the natural tactile feedback, augmenting on-body touch input with computer-generated tactile feedback can produce highly expressive interactions. And how can we do this? There are multiple approaches for augmenting on-body touch input with tactile feedback. The brute force or the most rudimentary approach is to place an actuator on the fingertip. However, this will diminish our natural tactile sensing capabilities. The second approach is to augment the fingertip with thin film electrotactile interfaces. For instance, a device such as Tactile, which is published in WIST 18. The drawback of this approach is that these devices have very limited mechanical robustness and can be destroyed over the course of numerous daily activities that our fingers perform. The third approach is to augment the skin with thin film electrotactile interfaces. However, this approach is not scalable and requires placing the devices at every location on the body where touch input needs to be performed. Instead of these approaches, we use the fingernails for providing tactile feedback by placing an actuator on it. This has several advantages. Firstly, it keeps the finger pad unencumbered. Secondly, it's highly scalable. That is, a single actuator is sufficient for rendering a click sensation for touch buttons pressed anywhere on the body. Finally, it has been used extensively in HCI research, and prior work has also shown that fingernails can be good locations for rendering highly articulate spatiotemporal patterns. This is a snippet showing how the actuator vibrates in response to touch input to provide tactile feedback. Taking this as our base, we conducted 3 psychophysical experiments to better understand the haptic augmentation of on-screen interfaces. Our first research question was, do users prefer tactile feedback for interaction on the skin? In the second study, we were interested in identifying the vibration intensity thresholds for rendering suitable tactile click sensations for on-body touch input. Finally, in the third study, we show that computer-generated tactile feedback can enhance the expressivity of on-body touch buttons. In the first study, we were interested to see if participants preferred augmenting tactile feedback for on-body touch input. For this, we fabricated a capacitive touch sensor and coupled the touch input with tactile feedback through actuation on the fingernail. We performed this under 2 interaction conditions. The first one is eyes-free condition, where there was visual feedback of touch input. Participants were blindfolded before performing touch input. The second feedback was a visual feedback condition, where a virtual button press was presented on a computer screen. We chose the first condition to be in line with situations where on-body touch input can be used for on-the-go eyes-free interaction. And the second condition to be in line with situations where on-body input is mapped to an off-skin display. And as you can see, our overall results show that participants prefer tactile feedback in all the conditions. In addition to the Likert scale readings, participants also provided valuable insights with regards to tactile feedback. Firstly, we fired the actuator at default intensity, and this was deemed too strong for on-body touch input. Secondly, participants also suggested that different tactile patterns can be used for producing variations in tactile feedback. And all the participants did highlight the importance of tactile feedback when they were performing touch input on the body. In the second study, we were interested in understanding the thresholds for rendering natural tactile click sensations. This is again coming in from the results of a first study where participants felt the intensity of the vibrations was too strong. In this study, we performed the experiment on 3 body locations because our body has varying levels of mechanoreceptor concentrations. We counterbalanced the order of presentation for body locations and used the method of limits to determine the thresholds. We used pulse width modulation to control the vibration intensity of the actuator. Results show that body locations do influence the thresholds. However, it is also interesting to note that the differences are not very drastic. In our third experiment, we wanted to understand the human capability of differentiating diverse tactile effects with a single actuator on the fingernail. For this, we chose 20 different tactile effects that are suitable for on-body touch buttons. We chose these rich tactile haptic effects from the TouchSense library, which is extensively used in literature for creating rich tactile effects. To the best of our knowledge, we are the first to employ non-metric multidimensional scaling, a classical psychophysics methodology in the context of on-body interaction. For the procedure, we had a control software where participants clustered the different effects based on their similarity. Each cluster had a bin, and participants had to group the effects in those bins based on how similar they were. After this, we performed multidimensional scaling to see the similarity or dissimilarity between those different effects. It is interesting to note that the baseline condition, which is on the right end of the spectrum, suggesting that there is always a distinct difference in the perception of augmenting tactile feedback. Secondly, it's also interesting to see that there is a family of soft tactile effects, and this was deemed suitable for providing subtle tactile feedback for text entry on the body. Overall, we show that actuation on the fingernail is a very promising approach for enhancing the expressivity of on-body interaction. However, there are a few limitations of our work. Firstly, we focused our studies on taps, which is most primitive touch interaction technique. Other widgets and interaction techniques such as sliders, pressure-based input need to be studied very thoroughly. Secondly, we used a vibrotactile ERM actuator, which is the most common and simple way of rendering tactile feedback. Other tactile feedback techniques such as electrotactile actuation also need to be explored and evaluated to see how they fit in for haptic augmentation of on-skin interfaces. Finally, we used capacitive sensing approach in this work. However, we believe that this technique of haptic augmentation can scale to other sensing techniques that allow for touch interaction on the body. To summarize, we proposed haptic augmentation of on-skin interfaces to increase the expressivity of on-body interaction. This work presents the first step in this direction and can be expanded to direct diverse input techniques on the body and is also scalable to diverse sensing technologies. Thank you, and I'm open to questions.